No, it has started. Dan, go. Sorry. My computer's really laggy. Sorry, everyone. Erica, would you like to kick us off more smoothly?
Luckily, nobody joins on time. So for those like 2 people who have joined on time, welcome to the Cambridge Skeptics live stream. We've done this before, trust us.
Sorry, Erica.
Oh, somebody, there's, yeah, you got
that was me.
You got it figured out. Right, everything's going really well. We're having a great time.
Chris doesn't even do this stuff, but in his absence, we're falling apart.
So, my name's Erica, and I am joining you here today with Andrew, Sam, and not Chris, because Chris is on a boat somewhere in the Atlantic or Mediterranean. We're not clear. And instead, we're joined by Ellen.
Hi.
The Cambridge Skeptics, we are a volunteer organization. We are dedicated to promoting critical thinking, science, and positive skepticism in our local community of Cambridge, but also across the UK and beyond. And today, I am going to be talking to you. And the topic that I want to bring is how to do an experiment. Before I get started, I wanted to ask you guys, before we did this experiment that we did together, and I'll give more details about that, had you guys ever done a science experiment before?
Yeah.
Yes.
Well, what did you do? What sorts of things have you done?
Do you want to go first, Ellen?
Yeah, so I got a bachelor's in psychology, in which I've done a few experiments. So my dissertation was on mood and memory, and don't ask me any more deals because I can't remember. Sorry to
No, that's good.
rubbish
But I
answer.
put you on the spot.
Mine's pretty much the same. I've done various experiments in psychology. I did, I can't remember either. I looked at basically how people's beliefs affect their perception. So showing people magic tricks and then getting them to fill in questionnaires about their beliefs in the supernatural and stuff like that, and seeing if there was a correlation between high levels of belief in the supernatural and actually seeing things differently. And there was actually, so that's quite interesting. But yeah.
Oh, Sam,
Awesome.
what about you?
Well, I'm a was sort of trained as a statistician at uni, and now work in finance where I do a lot of tests. So I work in insurance. We test different types of pricing, fraud prevention, debt prevention, affordability. We've got all sorts of things on trying to help the customer interact with the website more effectively. Marketing, treats. It's a smorgasbord of various tests, market tests, and pretty much all of it goes to my team. So
Awesome. Yeah, and I mean, so my background is I used to be an archaeologist. I was analyzing the chemistry of ancient bones and seeds. And archaeology is a bit of an interesting one because in some ways it's a little hard to do an experiment because it's not like you can get to ancient Roman settlements and like apply your intervention to one of them and test what happens and compare it to the other one. You end up trying to look for more natural comparisons of what's going on in archaeology and trying to build your hypothesis that way. It's very difficult to do a controlled experiment. The cases where I've done controlled experiments in the past have been where, say, like we have a theory about what's happening chemically with an ancient seed, and we set up an experiment to try to simulate what's happening in the environment, and then we'll test like, okay, this is what happens when we add this kind of chemical treatment versus that. So doing that kind of experiments. And then these days, pretty similar to Sam, I work for a company that does e-commerce, and we're doing experiments all the time. When we're looking at how people can best buy things online, we use science all the time. So for this this exercise, I wanted us to do a science experiment all together. And I thought of a scenario that I think, I was trying to come up with scenarios that everyone can relate to. The example that I came up with is, imagine you're out at a restaurant and the waiter brings you order a Coke Zero, and the waiter brings you a beverage and you're like, this isn't Coke Zero, this is regular Coke, or this is Pepsi. I can tell the difference. That was the thought that I had in my head. There are people, I thought, thinking about myself, I think lots of people might think, I can tell the difference between different types of cola. And I wonder if there's anyone in the chat who thinks, yes, I can tell the difference. I know that about myself. I can tell the difference between different types of, whether it's Pepsi and Coke, whether it's Coke or Coke Zero. I'd love to know if you think you are someone like that who can tell the difference between different beverages like that. So that was my starting position, was I wonder if this is a real thing. I wonder whether, in general, people can tell the difference. And then I started to extend this thinking. I also wondered maybe whether it applies to other types of food. So I thought another example, which was crisps. So, now I'm imagining this decision that you're making in the grocery store where you're like, oh God, should I buy the super fancy brand of crisps, or should I buy just the regular cheap, store-owned brand? Can anyone really tell the difference? And again, I'm sure that you guys, before you did the experiment, you were like, I definitely think that I know whether I can tell the difference. I'm gonna buy the posh brand because I know that it's a lot better. Things like that. So that was my starting point. The question is then how do you actually think about doing the experiment? So I've drawn some pictures to try to take you guys through what the logic is. And obviously you guys know, you guys all did the experiment with me, so you know how we ended up with the experimental design that we did, but I want to take you through what I was thinking. So I'm just going to share my screen. And you should be able to see it now. So we're doing taste test trials. This was us. This was the idea that I came up with for us to do a real science experiment together. And let's take the example of the posh crisps versus the store-owned brand, crisps. And yes, I do think that sour candies might influence your ability to taste test. A very good point from someone in the chat. So we've got these posh crisps and these sort of store brand crisps. Other brands are available. You can see, the posh ones are definitely more expensive. The cheap ones are actually sold in individual bags. So theoretically, you're even paying a premium to have them in individual packaging, and they're still much cheaper. So how you might approach this as an experiment is, can you tell the difference between them? So let's imagine you just hide the packaging. You hide it, you just label 1A and 1B. And your question to, and that's actually what we did in this experiment. So you can see on the bottom, I've got some crisps in a little glass dish, and there's a 1 labeled on the bottom. So you can't see the bag. All you can see is the 1. So this is you're your person. You are confronted with a sample that is A. You then make a guess as to whether it's cheap or not. In this case, the person guesses cheap. And then you're confronted with sample B. And maybe you guess cheap again. Now, this is where you want to think carefully about the experiment design. Because maybe it was posh. When you're in that moment and you're thinking, well, I know that it's going to be A or B. Well, how many of you would assume that the second one was going to be the opposite to the first one because it's only going to be one or the other, right?
If there's only 2,
yeah,
then yeah. Ultimately it's not much of an experiment if you go in and they're just both the same. So I think most people will have an expectation at the very least that the second one is going to be different to the first one if there's only 2.
Yeah, but actually that doesn't tell you. That only tells you half of the information that you think. because if you know what the second one is based on the first one, then you might as well not have had the second test at all, because you're only testing whether you could identify the first one correctly.
Yeah, because the second one is a given the first.
Yeah, exactly. And so that's that scenario here where you're saying, I know this one must be posh because I said the other one was cheap. So that would be an example of a bad experimental design. If you're saying to the people, like, listen, you know what the answers are going to be. You can work out what the answers are if you know what some of the answers are. It's a bit like...
Interestingly enough, if you've ever done the, is it the Pepsi Taste Chest Challenge they do in supermarkets sometimes?
Oh, yeah.
That's exactly how they do it. They give you 2 drinks and they say, well, can you tell which one's Pepsi and which one's our leading competitor or whatever? But it's always just two options.
Yep. And also think about a lot of like before and after product demos where they're like, oh, look, we use this like terrible cleaning cloth, and then we use this amazing shining cleaning cloth, and like, look what the difference is. And like, could you tell? Look, we revealed to the consumer which was the fancy brand and which was the cheap brand, and they were astonished. It's always this kind of scenario that they're replicating. Another really important factor is that the order in which you experience the samples can have a big effect on your opinion, especially whether it's about whether something is better or not. So we can't assume that you're equally likely to think that the first one is better or the second one is better. There will be like experimental factors that naturally lead people to assume that the second one is always better than the first one, regardless of which one they are, for example. So it's also really important in a test like this that you don't always do A, then B. Sometimes you do B, then A, because it can make a difference. So instead, think about it like you have an experimental slot. You have slot 1 and slot 2 in this case. And what you do is you just, in this case, there's 2 options. You literally just flip a coin to determine which sample goes in which slot. So you could have A, then B, you could have B, then A, you could have A and A, and you could have B and B. Those are all of the possible combinations. And you make it really clear to the people who are participating in your experiment that the information that they think they have based on the first sample does not tell them anything about the information that they have for the second sample. That way you're actually getting 2 independent data points. And the next question is, why stop at 2? You could have lots of experiment slots, right? Then once you have this methodology, actually you can extend it. And what that allows you to do, imagine we were testing Sam's ability to tell the difference between posh crisps and cheap crisps. And we give him just A and B, and he walks away and he gets them both right. Do we think that he's amazing forever?
Of course.
Between 1 and 2.
well, sorry. Yeah, between yeah, exactly. If he gets them both right, we're like, well, let's maybe test this a bit more to see whether there's a meaningful
But there's a 1 in 4 chance of that happening just through random chance.
Exactly. So let's like test it a little bit more. So you could extend this as far as you want. So this is what we did. I put crisps in little glass bowls and I labeled the samples 1 through 8. Now at this point, I realized I had a problem in the experiment. Do you guys remember what the problem was?
Yeah.
They look different.
They looked different. Yeah, exactly. So you can kind of see in the photo, the one on the very far left is slightly darker than the middle 3. And more importantly, I noticed that the premium brand crisps tended to have more of the potato peel on the exterior. And I thought, well, and then this is a really like important moment in science here, because I just saw Chris. Hi, Chris. It does need more beards. We're distinctly lacking in beards. Helen, if you could kind of just like wrap your hair around your face to make a beard, that I think would help.
We do have a fabulous ratio of gingers.
We do. We are upping the ginger quotient, which Chris sadly can't contribute to. But anyways, so at this moment, it's really important to think about the experimental design again. Let's go back to the scenario, the hypothetical, like a real life scenario that we're testing. So, do I want to test? Can somebody tell the difference visually between crisps? Or do I want to test whether someone can tell the difference taste-wise? And like, what would you guys think? Like, what's your preference as to which is the more interesting question to answer?
Definitely taste, I think.
For you, yeah.
Yep.
Okay, so like that was my opinion too. So what we're getting down to here is actually isolating some variables. We need to take the visual variable out of the equation so that we're only focusing on the taste variable. Now, we could run a separate experiment if we want and see, hey, can people identify the differences purely visually without tasting them too? We can do that if we want, but we need to isolate our variables and really get down to what is the one thing that we want to test. So what I did was I then put a tablecloth over all the samples and I labeled them on the outside so we can tell which one was which. And I asked everyone, you guys were there, and I was like, you have to take your crisp and eat it and put it in your mouth, but you're not allowed to look at it. You can't like inspect it before you put it in your mouth. You've gotta eat it without looking at it. And that was the experimental methodology. And here's everyone participating in the experiment. Everyone had index cards they were writing down their answers on. You can also see we've also got some glasses of cola on the side too, which was for the cola version of this experiment, which all obviously followed similar principles. Yeah, and so that was what we did. That was our experimental methodology setup.
So Erica, did you know which ones were which before we tasted the crisps?
Good question. Because what you're getting at is the idea of blinding, right?
Yeah.
Yeah, so people would have heard of the idea of a double-blind experiment. And Helen, what are the problems that might happen if I know the right answer?
You would give off like signals without realizing it to the participants.
It's Smart Handsome. No, it's not Smart Handsome. Clever Hands, the horse.
Yeah.
It could. Like whose handlers knew what the right answer. Like they gave him maths problems, but the handlers knew what the right answer was.
Oh, are you talking about the horse?
Yes. Yeah, and so the horse wasn't picking the right answer. He was picking the one his handlers got excited when he came near. And so when they sort of flipped it around and the handlers couldn't see the answer on the board, the horse did no better than average.
Mm-hmm.
Average, random.
And this is why, like, when in a context like this, it's not very serious. But imagine you're in a context where you have an animal who is making a detection of, say, whether there's blood matter in a person's apartment that indicates that they might have committed a crime. If the handler has any kind of a vibe that they are giving the animal about, like, oh, this was the boyfriend, therefore it's very likely to be whatever it is, there can be a lot of problems where people aren't fully blind to the circumstances that they're having to test. So in this
I appear to be glowing. I apologize. I'm trying to readjust the camera.
It's the
very
rapture.
angelic at the moment.
It's the rapture. They're coming for you.
Yep, exactly. Taking its time. I've been waiting for it for years. Yeah.
But in this case, Erica, not only were you sort of off to one side, not interacting with anyone, but we couldn't talk about our results, and you didn't know the results that we were putting down. So there wasn't you weren't looking at our answers and go. It was.
Yeah, exactly. So I wasn't in the room, like it was a big like kitchen living room thing, but I was off to one side. I didn't interact with anyone while they were doing the experiment. And yeah, you're right. I asked you guys not to interact with each other either. The closest that I got, I think, was to take the photo that I showed. But yeah, it's a really good point about blinding. So another question.
One more question, Erica.
Yeah.
So were the placement, I think you covered this, but I just want to check. Were the placement of the crisps completely random so that we knew that it wasn't going to be AB, AB. It was unlikely to be like that. Okay.
Yeah, exactly. So what I did actually when I was setting it up is if you guys remember, you guys were kind of milling around and talking to each other, and I went into another room and actually no, for the crisps I had it set up before you guys got there. So what I did was I took there you go.
Okay. The rapture's over.
The rapture's over. I used a random number generator on the internet, and for every bowl of crisps, I used the random number generator, and I had already decided that the posh one was 1 and the cheap one was 2, and so if it gave me a 1, I did posh. If it gave me a 2, I did cheap. And what I did was I wrote down, you have to record this. You write down which one you're doing separately. So I had that document saved in a like Google Doc or something, and so I was able to record it. But yeah, it was completely randomized, exactly what I said. I didn't use a literal coin. I used a random number generator, but the same thing. Yeah, good question. Any other questions about the way that we set up the experiment?
Not right now.
Cool. So, and I will say, everyone wrote down the results on pieces of card, things like that. So I still got the cards. Yes. And what I did was I entered the results in a random number generator. A spreadsheet. Why am I obsessed with random number generators? So what I want to do now is show you guys the results.
Cool.
What do you think?
Well,
cool. So I'm going to just quickly share my screen, and I'm going to share this Chrome tab here. So you guys should be seeing this tab, right? Awesome. So right now you're on the pop results. I'm just going to move us over to the crisps results, since this is the one we were talking about. So what I have done, I've just written down the sample number, the guess that the person wrote, what the correct answer was, and obviously in this case it was the same for everyone. So number 1, the correct one was always posh for everyone. Number 2, the correct one was always posh, etc. And then I just did a quick formula to show what it shows a 0 if the answer is wrong and a 1 if the answer is correct. So you guys with me so far?
I'm not, I'm sorry. So so I'm just looking at number 2 for participant C and
Yep.
Right, yeah, I'm with you. Sorry, I'm with you.
That's cool. So if it's a 0, that means the answer was wrong. So it means that these two are not the same. If these two are the same, it means the answer is right, and this is a 1. So now you're like, okay, but what does it mean? What were my results? What were the results of all of us on average? So have you guys ever done a pivot table before?
Yes, I love pivot tables.
Oh my god, I'm gonna do a pivot table. So excited. So we're just gonna do a pivot table to see the answers really quickly. And for the rows, I'm gonna do the participant, and for the columns, I'm gonna do the correct answer. And the values are gonna be my binary 0 or 1, was it correct? And then the sum isn't very meaningful. Instead, let's do the average. Because what the average tells us is if a person gets both of them, all 8 correct, then the average will be 1, which means they got 100% right. If they all got wrong, the average will be 0, because it'll all be zeros. And if they got 50% of them right, then the average will come out to 0.5. Wow. What are we seeing? What do you guys see?
I won.
I didn't.
It's
my blind chance whether I can tell the difference between posh and cheap crisps.
Yes.
I am a cheap date, it seems. Yeah.
And Sam apparently got all but one of them right. And Ellen, you were better than random chance. And Yasmin was was worse than random chance. So the question is, right now, do you guys walk away and be like, that's it? I'm terrible at crisps forever. Do we take Sam to a bunch of parties and be like, look at what this guy can do? Do you think that this, like, is this real?
It's difficult to tell. I mean, with those results you have there, you have, literally the full spectrum. You have one person getting everything right, and pretty much me getting 50-50 flip of a coin. So yeah, that doesn't really tell us anything. I mean, I guess it tells us that some people are maybe better than others, or it's all just random chance.
Go on.
Oh no, just there was one below. There were two bang on random chance, one just below and a couple above. So the gut feel is maybe there's a small, maybe a bit. Like it's not a dead cert that people can tell the difference. That's out. That option is no longer on the table. But there is an outstanding question as to whether we can, to what degree, how much differentiation.
Yeah.
Is there?
And that's really important, because what is this? Let's go back to what we're testing. We're testing whether people can tell the difference between posh and cheap crisps. Now the answer seems to be, on average, where this group in this experiment, are getting it right 60% of the time. So the question is that just due to random chance, or is there maybe a slight effect? Do we, on average, are we maybe slightly more likely to tell the difference between posh crisps and cheap ones? To answer that question, yes, there's statistics that we could use and there's math equations, but I don't know what they are. I would have to look them up. That's very boring. So another.
Sorry.
Hey.
The thing is, on the live stream, they can only see whoever's talking, so they can't see my deep judgment on my face. Yes, you do know the equations. I'm sure you do, but yes, you would like to work this through empirically. So
that's the thing. Let's work it out. Let's work it out ourselves. Let's find out together. So here's what we can do. Let's simulate what any person, what a random person could do just through a random chance. So I'm gonna make a new tab here, which is simulation, and I've got a participant here. We're gonna call them participant 1, and we're gonna give them a bunch of guesses. We're gonna give them guess 1, guess 2, etc., all the way up to guess 8. So then what we're gonna do? What are we gonna do in here? Anyone?
Flip a coin.
We're gonna flip a coin.
Yeah.
Because we're just going to simulate, like, what if they're guessing and they have zero ability to tell the difference between posh crisps and regular crisps, then it's literally just a coin flip in here. So I'm going to do.
So to go back briefly to our, secondary school statistics, you are defining the null hypothesis that there is no difference. People can't tell the difference between posh and regular crisps, which means that if they're guessing randomly, and therefore there's a 50-50 chance.
Yeah, that's
your null hypothesis. So if and then you want to test whether or not actually what we're seeing is actually people can tell the difference.
That's it. Yeah, that's just the Sam's going to be representing the voice of actual statisticians, and I will be representing the voice of people. Your statistics hat.
I don't have one.
Okay. Yeah, go on.
I have a question.
Yes.
About if you wanted more data, say it was like a more serious experiment, or if it was about something more serious, would you just get more participants and use this same exact experiment, or would you like branch out and get different brands of crisps, or would you get introduce more variables, or what would you do if you wanted more data?
That's a really, really good question. And the answer is that it depends what exactly you want to know. So, you know how I said before, like we've got to isolate some variables to figure out what the thing is that we want to test. Those different options that you presented are actually different ways that we could go into further detail. So maybe I want to test the idea that in general, people can tell the difference in general. If that's the case, then I should test multiple brands, right? However, maybe I work for one of these brands and I want to test the idea that my cheap version that I make for this one company is just as good as the premium brand. And maybe that's the idea that I want to test. In that case, maybe I would repeat the experiment only with those exact two comparisons again. And you can imagine the other question that you asked was about throwing in more variables. That you might want to do that again if you're testing generalization. I think also if you want to throw in more variables, it's really useful to have a reason why you're throwing in those additional variables. And this gets into something called p-hacking that you and I were talking about before we started the live stream.
Yeah.
Because there are like literally, and I mean this mathematically, an infinite number of variables that you could throw at this experiment. You could throw the variable about whether I blinked before I ate the crisp, or whether the wind was blowing from the west, or things like that. There are lots of variables that you could test. And if you are open, like if we're open theoretically to the idea that any of them could have an effect here, then we have no statistics anymore.
Yeah.
Because
so
anything could happen.
It's with a minimum number of with a limited number of true variables and an infinite number of spurious variables, like the likelihood of the number of false positives outweighs the number of true positives eventually if you just keep testing stuff. Sorry.
I think that's true.
So like if your hypothesis was that there's a gender difference, girls are better at tasting than boys, then you would just introduce that one variable of male versus female. But if you were to add in eye color and hair color and shoe size, you're more likely to get a significant significant results, but a false positive. Is that?
Are bearded people called Sam better at identifying crisps than the rest of us?
Yeah. And the thing is, like, you could do an experiment. Maybe you, on the basis of this experiment, you have a hypothesis that bearded people called Sam happen to be really good at tasting crisps. You could do the experiment and prove yourself false. I'm guessing that the answer would be false there, because we don't have a plausible mechanism for why that would be the case. But you'd have to do like an independent experiment looking at the statistics on its own. If you're going back and looking at things after the fact, you're much more likely to see something that's significant that's not really there.
Yeah, and there are ways of correcting it so that the overall likelihood of you getting, so rather than testing each variable on at a certain level, you test it so that the likelihood of all the variables collectively that you're testing are kind of at the same level. So there's corrections that you can do. It's we use it all the time at work's one for only correction. If people want to get to Fs.
Yeah, I remember that.
Although you still have to have an idea of what the number of comparisons you're making.
Oh yeah.
So having an infinite number of possibilities.
Well, there's an adjustment that can be done for just consecutive tests, but yeah, it's.
So anyways.
Anyway, going
back to the spreadsheet. Come on,
having tried not to do this the stats way, we've gone down the little stats rabbit hole.
But I think it's useful because people are used to hearing terms like statistical significance, and what we're going to go into here is actually what does that mean. So we have not the concept that we're exploring right now is this result 60% on average statistically significant? What that means mathematically is what are the odds of seeing this just through random chance? So we're going to look at what happens when we just let things happen randomly. And we're going to see, what are our odds of seeing this? We're going to actually just test a whole bunch of things randomly. We're going to use the spreadsheet to run a bunch of random experiments where nobody knows what the right answer is. We're just going to get them to flip coins. So here I've got my coin flipping function, which is between 0 and 1, and I'm going to extend that for all the guesses for this one participant. So you'll see, they got 0, they got it wrong, they got it right, they got it right, they got it wrong, right, wrong, right, wrong. That's what we're saying this one person hypothetically got. Now, you will see the random number generator refresh when I start adding more formulas. That's just a feature of the spreadsheet. And what I'll do is I'll copy it over so that it doesn't keep doing that, but it's regenerating the randomization every time. So just because the numbers are changing, it's still random. It's just a new flip of the coin every time, so don't worry about that. So what I'm going to do is I'm going to add additional participants. I'm going to run the experiment multiple times. And now what I'm going to do is I'm going to do it 500 times. So I'm going to take it all the way down to row 500. And actually, you'll see I'm going to take it just slightly beyond 500 for reasons that I'll explain later, but I'm only going to use up to row 500 in this case. So here, we've got 500 people participating in our experiment. And what I'm going to do is do what I said I was going to do. So I'm just going to copy this and paste the values, and then that way it's stable and won't keep changing what it is. So here I've got the raw results, just the numbers in the spreadsheet. They're not going to change. So this is our simulation. This is our random simulation. So what I can do is I can take an average of everyone's guess, and this is the results that we were seeing before, right? So this person got 62% of them right. Then we can just follow it all the way down to the bottom. Oh, you go too far, whatever. And we can see these are all of the averages, the average results for each of the 8 guesses that all of our 500 people in our experiment got. And if you can guess what we're going to do next, let me know.
Sum our average. So you get the average of the average.
Well, yeah, actually, why do we do that? Why don't we do that? Let's do that real quick down here. So I'll get my average and my average. Here we go. What do we see?
Pretty much.
It's 0.5. That's exactly what we would expect because we've just been flipping 504 times 8 coins.
Yeah, and before we get any potential pernicketiness, being exactly on 0.5 is less expected than being slightly off of 0.5. In the sense that it's just much less likely to be exactly on 0.5 than it is to be just in the general neighborhood
in
of
the general
0.5.
region. Yeah, and obviously the more samples that were in our simulation, the closer to 0.5 this value would get.
Yes.
Statistically speaking. The other thing that we can do for fun is we can just plot these results as a histogram. So you can see here, I'm going to make a nice little histogram. And what we're seeing is exactly what we were imagining. The values tend to be centered around 0.5, but there's some very extreme ones as low as 0 or even as high as 1. And I will say that that's very rare. So if you want to know what are the odds of getting, a 0 or a 1, it's hard to be sure with small numbers like this. You would want to extend the simulation and get have larger numbers here. Yeah.
It's about 1 in 250. So with 500 having one of each.
Yeah, that's about what you'd expect. But again, you've worked it out mathematically. Yes, if you were trying to work it out just from a simulation, you'd want to have larger numbers in here to really be sure that, because just when you're seeing one number, it's hard to know whether that was on its own due to random chance. And that's getting to the theory of what I want to talk about. So imagine the result that we were looking at was 100%. Imagine that in our results here, imagine that this number was 100, was 1 rather. Imagine that all of these were perfect, that we got a perfect score. Using words like unlikely or likely, would you say, looking at this simulation, that it is likely or unlikely?
Unlikely.
Deeply unlikely.
Deeply unlikely. Very, 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 very unlikely.
Due to random chance.
Due to random chance. Exactly. Now, that's not what happened. So you can imagine, okay, getting the result of 1 of everything perfect is very rare. What about getting 0.875 of them right? Well, that's a little bit more likely.
Yeah.
But whereas what was our number? Our number
That's
was
60,
over here.
sorry.
Yeah, exactly. Now, one thing you might have noticed is that we're missing some numbers here. This is not very granular. Our exact number of 60 actually doesn't appear in this list because we were averaging a group of 5 people, whereas here we're just looking at one person's results on their own. So let me instead do the average of 5. So what we're going to do is just take the average of 5 people's answers, 1, 2, 3, 4, 5, and we can fill it in. And now you can see why I put those extra couple of rows on the bottom, so that the 500th person here has a full list of random people to be part of a team with. So I can just delete these technically because they're not. Oh, sorry, it should be 501.
Yeah.
I'll do that because there's a header row. So 501 is our 500th sample. There. So when I make the histogram of this group, it didn't do me an automatic histogram that time. You can see that it's a little bit more filled in. Still not great, still looking a little lumpy, but there's more bars in this histogram than there were in the previous one that I showed.
Yeah, and
so now,
it's
well,
and also it's more clustered towards 0.5, which
is
because in essence we're sampling more, you'd expect it to be closer. Because if you don't do 1, everyone's either at 0 or at 1, so you end up with 2 bars right at the edges. You do 2, half the people are going to get 1 right and 1 wrong, and then the quarter each. And so as you end up more and more samples, it ends up getting closer and closer and closer to the center.
Yeah, exactly. So remember, like before, our extremes were 0 and 1. Now the range on the x-axis is more close to 0.5. The question is, though, like, how do we talk about the idea that, okay, the result that we got was around here, was 0.6? How do we describe? We talked about how, like, my question for you guys is, what words would you use to describe how likely you think this result is to be due to random chance?
So if we're taking the middle of this graph as random chance.
Yeah. Well, this whole no. Let me take this. We generated this from a simulation. This whole graph is a random chance.
Okay. Right. Okay.
The question is, our result is over here at 0.6. This is what we got in real life. My question for you is, how would you describe the odds of this being due to random chance? Our result being due to random chance?
I'd say fairly likely to random chance. I mean, it's not that far away. It's, I mean, it maybe indicates that some of us have slightly more discerning taste. You know, there might be.
We'll get into that. We'll get into whether there's some individual variations. That's really good.
Might be something to the idea that there is a difference, but it's very subtle.
Yeah.
Maybe that, but I'd still say it's fairly close to being just random chance.
About the taste test, there was definitely a difference between the cheap and expensive crisps. There was like a different taste and also a different texture, and I think most of us.
So you did a lot better than me. I didn't pick that up, as you can see by my results. But
Yeah, but most of us got that there was a difference between the crisps.
Yeah,
But what we didn't get was that some of us thought,
different.
yeah, it was hard to tell which was which. You know, I might have got that there was a difference between the cheap and the expensive because they tasted and felt different. But I
Yeah,
might have thought that it was the other way around.
I see. I see
Or
what you're
Andrew
saying.
might have because he got more wrong. But
I have no idea.
that might be
Yeah,
an
yeah, yeah.
explanation for why a lot of the answers were wrong, not because
Oh, that's a really good point. So you're saying that you might have been correctly able to identify that sample 1 was the same as sample 2, and sample 2 was the same as sample 3, and then sample 2 was the same as sample 3. You might have been correctly able to identify that all 3 of those were the same, but you mislabeled them all
Yes.
as cheap.
yeah, well, it couldn't
Yeah.
have been all of them because then we would have got 0 if we
Well,
got them all. But you know what I mean, that
yeah.
it might have been that we just got it the other way around for a lot of them, or some. Yeah, you've got what I meant.
Yeah.
There is a taste test hypothesis whereby you get you have 2 types and 3 samples, and you're told basically asked which one's the odd one out, rather than which one is this and which one is that.
Which
to kind of help with
maybe that would have been a better. So almost like what you're saying is there's another variable to isolate, which is, can you tell the difference? And that variable is actually more fundamental than, can you then assign that difference to the correct category?
I think that for me very much was the case in the other test we're going to come on to. With
I was going to say
the drinks,
for me too.
Because I don't drink any of the 3 drinks we were testing normally. I didn't have a baseline to say, okay, this is what Coke tastes like, therefore I'll compare it to other things. So I think I very much mislabeled things. So it'd be interesting to see if my mislabeling was consistent.
So for the Coke Zero versus Pepsi test, we could have, the questions could have been, which one do you like, which one do you dislike, or which one is sweeter and which one's less sweet.
Yeah. Well, so this, the way that we're analyzing the results here is not going to give us that answer. And it's, I think it still works given the way that the experiment was presented, which is, can you tell the difference between pot and cheap? So it was presented as a labeling exercise, not as a can you tell if the 2 are the same? But what I think we need to do though is, and I'm not set up to do this right now, is look at the data and test whether your hypothesis is true in the data. If what you're saying is correct, we should be able to query the data in such a way that gives us that information. So I'll take that away and come back. But for now, I want to assume that that factor is not a factor, that you were approaching each sample independently and go through and come up with a, so Andrew was talking about like what words we use to describe how likely this is. There's another way that we can do it, which is, I'll just take these results, the same results that made up this histogram that we're looking at. I'll take them, I'm going to put them over here and just paste the values so that they don't move around. And I'm going to sort the data. And the data has a header, so I'm going to sort them from smallest to largest. So we can see that this sample, 0.25, this was so there's 2 of them, 0.225. This was the smallest results that our simulation got out of a group of 500. And if we go to the very bottom, you can see that we got the highest result that we got out of 500 was 0.75. Now let's look at our results. Our results for 0.6, the lowest value starts here, and that's at row number 438, which means that in our order of samples that we've ordered here, our order of simulations, it was number 437, because we subtract 1 for the header. So what we can do is we can divide that number by 500, because it was 437th out of 500, which gets us 87%. And what's that saying is that 87% of our simulations were smaller than this number. Or if we subtract 1, if we subtract it from 1, you can make it as a percentage. 12% of the samples were more extreme than this, or were equal to or more extreme. So we can actually put a percentage on what Andrew was saying, but it's not very likely. What this is saying is that when we simulated the results, there was about a 12% chance of this just being due to random chance.
Yeah.
So the question for you guys is that result meaningful? How do you interpret that?
I mean, my gut reaction to that is only 12% chance of it being, random. That seems important. That is, it's
That's not bad.
It's not bad. There are various gambling things where you get less chance than that.
Yeah.
So I would say, effectively 1 in 10 chance of it being random. That seems pretty good to me at face value.
Yeah. And this is where, so this statistic that we're talking about here, this is the probability of it being due to random chance. This is the exact same thing as the p-value. When you hear stats papers or science papers being reported and talk about the p-value, this is the p-value. The probability, p stands for probability, the probability of this being due to random chance is about 12%.
It's part of me is saying like there's a few different like considerations here, and so like if you're thinking, should I publish it, then I don't know that we're necessarily doing the right test, because ultimately if your conclusion was people can tell posh crisps from naff crisps, you'd publish that. You'd also publish it if it was like people can't tell the difference. In fact, they think all the posh crisps are naff crisps, or naff crisps are posh crisps. And so in that case, you'd need to look at both ends. Like, when we're doing this, we're kind of going 12.5% of cases are this extreme or more in the positive, in the kind of positive side.
You'd also have to look at 0.4. You'd have to look at the other way. So you'd have to like do the mirror image. So you'd have to count row 85, so number 84 to the end. And then you're talking about what are the odds of it being this low or this high?
Yes. Yeah. Yeah. And that ends up being
it effectively doubles this number.
Yeah. So that's on one side. The other side is, of course, that where your cutoff is for what you're going to declare significant, what you can then sort of draw a conclusion from, really depends on how crucial it is that you get it right. So if hey, should I buy the posh crisps because my guests will notice them? That's a relatively low threshold. Like, worst comes to worst, you're out a quid or two. If you're trying to decide on whether you want to throw out your current model of physics and create a new one, then you need, that's a really high bar, which is why physicists use, 1 in millions, 1 in billions, rather than 1 in 8, which is, where we were. So it really does depend on your kind of your appetite for being wrong as to whether or not you can declare something like that significant.
And that's why having an arbitrary threshold at which you decide to publish something or not is not useful. The p-value is just a continuum, like we showed here. If our results had been slightly different, the p-value would have been slightly different. 0.5 isn't a magical threshold, which is a problem in experimentation. Now I want to show you one other thing, which is, remember Sam and his magical ability to guess the crisps correctly. So if we look at Sam's results, over here, it was 87% correct. My question for you guys is, how could we apply the same technique to figure out whether he's magical? I'll give you a head start. So remember this column here. This is our average of every individual person, what they guessed. So Sam could be one of these people, right? So we could do the exact same method. We could say, okay, I'm going to take this. I'm just going to paste it over here to make it clean. I'm going to paste the values, and we can do the exact same thing where we sort it with the header. And look, we've got it all nicely sorted, and we're going to scroll. Oh, I'm out of columns. We're going to scroll all the way down to 0.875. Up here we are, all the way down. And what do we see? 490 out of 500. So that means if I take 1 minus 490 out of 500, 2%. There's a 2% chance that any random person in this 500-person simulation could be this awesome.
Which would be statistically significant?
Yeah.
Yeah, in most.
Now the question is, can you guys spot what's wrong with that?
We're picking one person out of 500. So,
Well, you're
out of
picking
5.
one person out of
out
the
of 5, sorry.
Yes, exactly. So the question isn't what are the odds?
Magical.
It's not the question whether it's the question whether one person out of 5 could be magical.
Okay, so would you have to divide that value by your p-value by 5?
There are things that you could do mathematically, but this is where the Bonferroni correction comes in.
Yeah.
But let's simulate it instead because it's more fun. So instead, this is how we'll do it. What I really want to know is, so this is my group of 5 people here, right? My 5 people who've responded to the one experiment. What I want to know is, what's the highest value in this group, right? Who is the Sam in this group? What's the value for the Sam in this group? So I'm going to do max 5. I'm going to call it max 5. And I'm just going to take the max of, again, these 5 people's averages, 2, 3, 4, 5. And I'm going to do that all the way down. So I've got this nice long list. I am then going to add some more rows to my spreadsheet columns. And I'm going to paste some special values there. So I think I might have forgotten to delete my extra rows off the bottom. But anyways, I go sort my range with my header, blah, blah, blah. And now we can see, sorry, am I scrolling back too crazy? Now we can see, scrolling down here, that Sam's 0.875 is now showing up in row 423.
Okay.
So now if I take 1 minus 422, because we subtract 1, it's now a 15% chance. Sam's way less special than we thought he was before.
Yeah. So, but to be explicit, yeah, 15.6% of the simulated runs that we did had the highest person out of the group of 5 getting 87.5 or higher. That was the thing, because it's self-selecting. The highest, whoever was highest was the one that we were choosing. So it didn't matter. Rather than, and it's Erica, you tell us which fallacy it is. Sorry, I don't want to steal your thunder.
So this is the lottery fallacy. It's the idea is we go from saying what are the odds of Sam winning the lottery to what are the odds of anyone winning the lottery. We know we wanted to calculate what are the odds of someone in the group of 5 having an extremely successful result, not just the odds of any one person off the street, because that's not how we did the experiment. So
I don't want to rush you, Erica, because this is really interesting. I'm finding it, but it is now 7 o'clock, and we normally end it after an hour. So if you want to, 8 o'clock, sorry. If you want to, I don't know if you want to jump onto the pop results.
Well, that's what I was going to say. I want to quickly show you what the results for the pop one was, but I won't take you through all the results. So I'm going to take you to another version of the spreadsheet called Here's One I prepared earlier. And you can see there's all sorts of stuff in here. What we've got here is the results from the POP test. And I will say Sam didn't participate in the POP one because we were busy doing something, I don't know, making pizzas or whatever. But we've got the same correct yes, no. The POP one is slightly different.
I got them all wrong.
You did get them all wrong. The POP one is slightly different because we actually had 3 options, not 2. And we used 6 samples rather than 8. But the exact same randomization occurred, the sort of labeling, things like that. The other thing that happened is we had 2 sets of glasses rather than 1 set. Like how everyone was drinking, everyone was grabbing crisps out of the same bowl. People were not drinking out of the same glass. We had couples sharing glasses. Yeah, exactly. You know, COVID and all that. So what I did, and you can see the exact same pivot table that we did before. So Andrew, with his very unsuccessful results, Yasmin was apparently very good at guessing different kind of beverages. And we've done the exact same simulation that I did before. This time I had to modify the equation slightly of randomization so that there was only a 1 in 3 shot of getting the answer right rather than a 1 in 2. But the math works out the same. So I did the exact same randomization. And I then took averages of a group of 4 rather than averages of a group of 5. And when we ordered the results again, remember our result was we got 3.75% correct. Now we would expect
0.375, correct.
Sorry, 0.375. We would expect 0.33, or these are out of 1. I said percent, I didn't mean to.
Yeah, 0.3.
33% of the time, what we'd expect it to be right just through random chance. We got it right 38% of the time. So the question is that statistically significant? So we go over here to my average for the group of 4. We look for where we get to 0.375, and we can see, based on the math that I've already prepared, that this has a 31% chance of just happening due to random chance. That's not very good, is it? No.
Okay.
But now, my p-hacking friends, what if we delete Andrew?
Yay!
Being useless.
So if we delete Andrew and we redo the pivot table, or we just recalculate the average, actually, we can just do that. The average of all of these samples is 0.5. So we go from an average of 0.375 to an average of 0.5. So we massively improve our chances by getting rid of Andrew's results.
Get rid of the outliers.
Yeah,
It's about,
exactly.
It's about 3 times as high above the random sample as you'd expect.
Yeah, so now we go over here to my ordered list of simulations. I get to the first 0.5, which is at row 478. So we get to we get to 1 minus 477 over 500, which is 5%. Sorry, so we've got a p below 0.5 if that's the threshold that you want to use. So just by getting rid of Andrew, we've apparently got the ability to tell the difference. Sam.
But that number is still based on simulating groups of 4, not groups of 3.
Ah, good point, good point. I have to redo that. Sam, off the top of your head, what would the effect be?
Because you would expect that number to go up, so it would be higher than 0.46 because you'd have a smaller sample and therefore greater variation.
Yeah, you're right. Let me redo that really quickly. Average of group of 3, average. Oh, I don't need you guys. There we go, autofill. Aren't spreadsheets fun? And then we're going to paste these special values. I'm going to move them over actually because I'm going to lose my calculations. Values only, data sort, header. And then we're looking for 0.5. There we go. Thank you for doing my math better. So we get 464. So 1 minus 463 over 500. 0.7. That's still pretty a big difference in significance. just by removing Andrew's result.
Yep. And other things we could do if we wanted to, either on this or on the other, is have a look at the individual samples and go, oh, well, actually, crisp bucket 3 was clearly full of unusual crisps because everybody got it right or everybody got it wrong. So we could remove that sample. And yeah, as Ellen, I think, touched on earlier, we could start splitting it by lots of different variables and say, well, actually, bearded men are terrible at crisps and with, so on, or there's all sorts of weird stuff you can do where you decide you're going to sample from your own data and use that to create a false larger sample.
But the question that I have for you guys is it right to exclude Andrew? Not a general search, just from this experiment.
Just throw me out of any test I'm involved in and you'll probably get better results.
Obviously it's right to exclude Andrew.
I would say there's probably only 2 scenarios under which it would be okay to exclude Andrew. And one is if he's a bad actor, deliberately getting things wrong, and the other one if there is
marvelous actor,
some reason why he wouldn't be able to determine it. So if, for example, he had blown all of his taste buds off with sour candies, then it'd be like, okay, among people that can taste, but you would still need to qualify your conclusion. If there is, you've got some reason to exclude them.
Yeah. Does anyone else have a similar opinion or a different opinion? Andrew, do you think
I remember when I was doing experiments, doing statistics, there were ways you would deal with outliers. So if you had people who were, extremely out of the norm, so you'd sort of map your data onto a graph, you'd work out your means and things like that, and then you'd be able to calculate whether values were significantly outside of the norm. And now we were sort of shown that was a time where you can kind of get rid of outliers, but from what Sam's saying, that's still a result. I think some of the arguments would be things like you said with the bad actor. So you have someone turn up to do your experiment who's not really interested and just puts anything down and doesn't really take it seriously. And so you might end up getting a result from them that is very much outside of the norm. But I guess, do you have to then prove they're a bad actor? Is it enough to just...
Oh.
It's unless you... I think that from a professional point of view, you'd want a relatively high threshold, or else you're just going to be shaping your data to fit your conclusions rather than your conclusions to fit your data.
So that's really important. I think that whatever you do, your outlier methodology must be determined before you see your data.
Absolutely. Yeah.
If you're deciding, like we did right here, if we're deciding to exclude Andrew after we saw his results, that's a really bad practice. That's what leads to p-hacking. That's what leads to results.
Accidental p-hacking.
Accidental p-hacking.
Whereas for most of my life, I'm excluded before things take place. Yeah.
Well, there you go. But it's really important.
Yeah, but there are good reasons. I volunteered for an experiment that actually was searching for volunteers at a Cambridge Skeptics event a couple of years ago, where I had a load of nodes stuck to my head and basically had to do connotations. So basically they were looking to see if there was a link between, I think it was biases and prejudices and religiosity. So I was part of the atheist sample, whereby I sit down and go, okay, well, what do you think of, I can't remember exactly what it was, but basically I had a computer screen. I had to kind of say how I responded to various phrases and things about immigrants' backgrounds, basically all sorts of demographics, and they were monitoring my brain. And because you're selecting hundreds of results, I was there for hours and I started getting sleepy as I was going through it. And I don't know if that screwed up their readings, quite possibly. But there are legitimate reasons to get rid of it. But if they're doing it, if they're doing it correctly, it must have been, okay, here are the potential issues on the experiment, here are the criteria under which we'll be
That's
excluding
the
people,
thing.
and therefore we're going to put it carefully within the body of what of the text, but also sort of couch any kind of results in this context.
And what's important there is that they have a reason to exclude you. Maybe it makes sense in psychology. I was never trained in stats for psychology, but it might make sense that if you want an assumption that you want your conclusions to apply to a typical population, that anyone who is extremely deviant in how they perform on the test might have other unseen, like confounding factors, like other attributes about themselves that you would have excluded them from the test if you had known about them, but it wasn't possible to test for these things. So therefore you have a policy of removing extreme values. That's there's nothing inherently wrong with that method, but what it does is it affects how you then go on to generalize your results. And everything that we do, there's difficult decisions to make. When I was in archaeology and I was analyzing the isotope ratios coming out of a mass spectrometer, I had a very clear protocol for removing outliers, and it was equally important that if I had a weird result and I couldn't explain, like chemically, why it was a weird result, I had to include it. Like if I had zero evidence to explain, like there wasn't, like in the mass spectrometer, there's all sorts of chemistry going on, and there's lots of data that you get about how the sample goes through that chemical process. I'm getting lots of numbers. If all of those numbers are fine, my only conclusion is that that is genuine, and I have to then incorporate that into my theory of how people ate in the past, which is quite interesting.
Cool.
Yeah. So that was all I wanted to share with you guys.
Yeah, I think that's probably a good place to end. I mean, I've got lots of other questions about different things, but I think maybe we can address them another time. So things like
Absolutely.
publication bias, the file drawer effect, the fact that, to sum those up, people who don't know, basically, if you're not finding significant results, a lot of places won't publish those. And so you have this idea that when you look at scientific journals, that the results on people being able to tell the difference between Coke and Diet Coke and all that lot is significant because those are the results that get published. But then there's 20 other tests that show that they weren't significant, which didn't get published.
Exactly.
And so you have...
to a great extent, the tests themselves are a test. And so, each, as we've sort of shown here, where we were grouping, or we were doing, simulating a person, then simulating the group as being a sort of separate thing. Yeah, the tests are themselves a test. So anything that has, a 1 in 20, p-value of 0.95, so 1 in 20 is going to be wrong. We'll do that 20 times. One of them's going to, on average, one of them's going to come out positive. Which is why there's calls for like the all studies projects, where every single study response is finding is published, regardless whether it's positive or negative, because then you can see the whole body of tests on a single subject rather than just that which gets published.
Yeah, exactly. But yeah,
well, that's on that very quickly. Well done.
But yeah, I hope you guys like thanks so much for doing this experiment with me, because it was really fun. And I enjoyed like going through the numbers and thinking it's interesting to apply the scientific method to like a really tiny problem, because you actually do get to use the whole scientific method, which I enjoy. So
and the take-home message is, if you ever go to Erica's house and ask for a drink,
very complicated.
You know what to expect. You're going to get six glasses of drink and have to guess which one's which.
Yeah, and speaking of which, like, when do you guys want to come over? Yeah, you're like, never again after that. But like, so that's all we wanted to do now. Andrew, what are we doing next?
Oh, right. So next time, in 2 weeks' time, we're going to be looking at false memories and the Mandela effect. So I'm hoping that'll be interesting.
Sounds great. In the meantime, leave us a comment, join us on Facebook, subscribe to our channel. We'd love to hear from you if you have suggestions for topics you would like to hear about. That's all from us. Thanks very much for joining.